Right, I think I'm gonna get started. Good afternoon, everybody. I guess it's afternoon. Sorry, I'm just back from across the world and I still don't know what time it is. But anyway, welcome to the AstroAI seminar. I'm very happy to introduce today Ruo-Yu Shang from Barnard College and Columbia University. He and I have been in contact regarding potential collaborations that makes his interest in very high energy astrophysics with machine learning. And I'm happy to have a speaker on the topic because I don't think we've had a lot of talks covering gamma rays. Ruo-Yu is currently a postdoc in Barnard and Columbia University. Before that, he was postdoc in UCLA, and he got his PhD from University of Illinois in Urbana-Champaign. And today he will be telling us about machine learning for gamma ray astrophysics. So, floor is yours. Thanks so much.
Thank you, Rafael, for the introduction. Okay.
And I encourage everyone to interrupt with questions. If you have any during the talk, you have the full book.
Yes, my presentation is going to be very flexible, so just stop me anytime if you have a question. Okay, so, well, you see the title is Machine Learning for Gamma Ray Astrophysics. Before we start, this is an outline for my presentation today. So first, I will give you a very brief introduction to the gamma ray astronomy. I will briefly talk about the future observatory that is planned, this Cherenkov Telescope Array Observatory. And then I will then talk about a few projects that I'm currently working on, including this machine learning for a lower level data analysis to remove noise in the data. And then I will talk about the things that I am interested in is the time domain gamma ray astronomy. This is very close to Rafael, the subjects that Rafael is also interested in, but in X-ray time domain astrophysics. I will talk about the challenge for the gamma ray time domain astronomy and what potential solutions that AI and machine learning can provide. And I will also talk about other people's work. People have been applying machine learning techniques to things like event reconstruction and background injection. So this is an overview for today's talk. Okay, so for the ground-based gamma astronomy, for ground-based today, I'm focusing on this technology called imaging atmospheric Cherenkov Telescope, or IACT. We have very energetic events sources that accelerate particles to TeV or even PeV energies. And these sources, they send very high energy photons to Earth for gamma ray, and just like X-ray, because their energy is very high, they do not survive on the ground. They will be stopped by the atmosphere. So the way this ground-based gamma ray telescope operates is instead of detecting the gamma ray directly, we detect gamma ray indirectly through the secondary interactions that happens in the atmosphere. So you have a high energy gamma ray entering the atmosphere, and this gamma ray is colliding with molecules in the atmosphere and creates energetic cascades, a chain reaction of secondary particle productions in the air. And this cascades of high energy particles, they create, because in the air, they can move faster than the speed of light in the air. And this produces a Cherenkov radiation. It's basically a shock wave in radiation. So by detecting this shock wave, we can then reconstruct the incoming direction of the gamma ray. And this is how IACT works for gamma ray. Okay, so just to give you some idea how the image of the gamma ray shower look like. So this is a shower from a gamma ray. Gamma ray enters the atmosphere and then interact with the molecule. This interaction creates a chain reaction of particle productions that creates this shower. And then this shower emits Cherenkov radiation. And then you build this huge, sorry, this resolution is just terrible. I just realized that if you expand it to the size, it's not a great picture, but you have this huge shining reflector to collect the Cherenkov radiation produced by this shower, and you project this Cherenkov radiation onto your camera. And this is what you see is an image of this shower. And this image is actually not stationary. It's a motion. It's an evolution of this shower in the air. So you can actually see this is in the snapshots of this air shower as it develops through the air. You can actually see the trace of the gamma ray shower. So if you follow the trace of the image that you collected on the camera, then you can basically follow this axis of the shower, and this axis points back to some location in the sky that tells you where this gamma is originated.
So what sort of detectors do you need for that? What sort of detectors do you need in the telescope?
You mean the type of the camera, or?
Yeah, what type of detector does it
So
use?
conventionally, people use PMD, and more recent development, people start using silicon PM camera that can give you more compact, higher resolution pixels that you can, yes.
How often do you take the snapshots?
How often is usually, right, so from start to the end, this whole process spends around like roughly about 100 nanoseconds. And you can digitize this trace 1 nanosecond per frame. Okay, so a little more detail how you do the reconstruction. So for a shower, you put the mirror here and you see an image of the shower. And just like I mentioned before, if you follow the trace, if you follow the axis, this axis will lead to the source of the gamma ray source in the sky. However, you cannot do this with just one telescope because you know you can find an axis of this image, the primary axis, but the source can be anywhere along this axis. To really find the location of the gamma ray shower, you actually need at least 2 telescopes. This is just like you have a pair of eyes, you have 2 eyes, you see the same object from slightly different angles that give you 2 different images. And this difference in the 2 images tells you the 3-dimensional distance from you to the source. So you actually need 2 telescopes. And if you overlay the shower image seen by 2 different telescopes at 2 different locations, and you follow the axis of each of the image, and then the intersection points tells you the exact coordinates of the gamma ray source in the sky. So for this type of technology to work, you need not just 1 telescope, you need an array, you need multiple telescopes. For the current generation telescopes, that includes Veritas here in the USA, Magic in the La Palma Island in Spain, or the HES Observatory in Namibia. So all these 3 major current generation observatories, they are arrays of telescopes. So for example, Veritas has 4 telescopes, Magic has 2, and HES has 5 telescopes. So these type of technology covers the gamma ray astronomy with an energy range spanning from roughly around starting from 100 GeV to about 10 PeV. And for the next generation observatory, these three major gamma ray observatories, people are coming together, they put their resources together to collaborate to build a much larger array for the next generation. So this is the Cherenkov Telescope, Cherenkov Telescope Array Observatory, or CTAO. This is a global effort aiming to increase the gamma ray detection sensitivity by at least a factor of 10. So this is not a real photo. This is some vision for what it should look like for the next generation telescope array. The current array is already under construction, and we expect the so because this is a huge array, so there's no like a clear date of when this array will be operational. The operation will be gradually happening. Once you have a few telescopes, the array can already function, and you can start to work with like 3 or 4 telescopes at the beginning, and as time progress, more and more telescopes will be constructed, and this array will then become more and more complete. But we expect this the observatory will start function in the next few years. Actually, in this, so the observatory will cover 2 sites, one in the northern hemisphere, another in the southern hemisphere. The one in the northern hemisphere is already partially operational with maybe point can remind how many.
It is an industry that is already out of production.
Yeah.
And it's already producing like
Right. Right.
And the other 3 industries, because there will be 4 industries now, are already in construction. So they will be finished in this year.
Okay.
So there will be 4 industries.
Thanks for the information. Okay, so as you have seen from this picture, there are multiple types of telescopes in this CTA array. So the CTA will cover a really wide energy range from about 200 GeV. The lowest energy is covered by this large-sized telescope, all the way to the highest energy, about 300 TeV by the small-sized telescope. So you might wonder why we need different sized telescopes, because for low energy shower, the gamma ray energy is low, and the gamma ray can only like produce smaller shower that give you like a really faint emission. So for this type of events, you need a very huge reflector to collect all the faint Cherenkov emission from the source. For high energy shower, you don't need a really huge reflector to collect Cherenkov light. What you need is a large effective area. This is because usually these astrophysical sources, the spectra of the particles are usually following some kind of power law. So as you go to very high energy, the event rates drops very quickly. And so you need a lot of telescopes that covers a huge area of land to get in order to increase your detector volume. So you can build smaller telescopes to and a lot of small telescopes to cover a huge area of land.
So what ends up deciding on the sensitivity of the instrument? Is it also total collecting area? That you know this telescope will be more sensitive because the total collecting area is larger?
Yeah, that's one factor.
Okay.
That's true. Effective area is maybe the largest factor to determine the sensitivity. There are other factors too, like you can improve the camera and optical system to improve, for example, the angular resolution of the gamma ray. If you have good angular resolution, that means you can separate signal and background better. That will give you another boost in the analysis efficiency. That will also improve the sensitivity. Okay, so this is a project that I am currently working on, is to use machine learning technique to do some lower level analysis. This is about removing the noise from the data. So about the noise. So the IECT operates by detecting the Cherenkov radiation from the gamma ray shower, and this plot is showing you the emission spectrum from the Cherenkov radiation. The Cherenkov radiation basically follow this red curve. It scales like the wavelengths square inverse. And sorry, the peak of the spectrum occurs roughly at about 300 nanometer. And this signal is corrupted, is buried in background noise. And this is an example of the background noise spectrum that we collected from data. You can see there are multiple line emissions. There are for example, the atomic airflow emission from the atmosphere that gives you these lines. There are also components from, for example, galactic plane, or even the light pollution from distant cities. So as you can see, there's no the contribution for this background is unknown and is dynamic. It can change from night to night, or even from hour to hour. So basically, I'm trying to say the source or the spectrum of the noise is uncertain, it's very dynamic. And there's another layer of complexity to this noise, is that we have many different types of telescopes with different camera designs, different optics, and they all respond differently to the noise. So we need, it will be ideal to have some kind of universal algorithm to remove the noise contamination from the Cherenkov signal. So conventionally, how is this done with a conventional method? So this is an example of the Cherenkov image. You have a shower image here, but it's contaminated, it's corrupted by the noise fluctuation from the night sky background. And the traditional method would define a signal region. For example, you put a mask to block the Cherenkov image, the shower image, and you calculate the noise fluctuation in the background region. And then from this fluctuation, you calculate RMS, for example, then you can set a signal threshold based on the fluctuation in the background. And then you only keep the pixels that pass this threshold. And well, there are more sophisticated way that you can define, for example, two level thresholds in order to keep more pixels from the source and reject more background. But the idea is very simple. You calculate fluctuation from background region, and you only keep the pixels that pass this threshold. That method works fine if you have really bright signal, but if you have some really weak signal from low energy shower, then that method would be not very efficient. For example, this is a simulation. You can maybe tell there's a very weak shower here, and it's buried in very noisy background. This is in simulation, so I can show you this is the true signal image. And if we apply this conventional method, calculate the fluctuation in the background, this is what you get. So as you can tell, we failed to keep the majority of the signal pixel from the shower, and there are a few noisy pixel in the background that also pass through class. So this conventional method is problematic, it's not yes.
Originally, when you were talking about how to promote telescopes and getting the information from there, it sounded like the main information that we needed was the direction of the signal. How important is it to accurately get all of these pixels and correctly get the signal of each pixel, in your truth image.
Yeah, yes, so if we take this as an example, if you take all these pixels as your signal, and you try to find a major axis, you do PCA, you find a principal component, this will screw up with this direction reconstruction, because these large noisy pixel that is far from the true image, that will destroy your reconstruction. And also, it's not just about direction reconstruction, we also reconstruct the energy of the shower from the brightness and morphology of the shower. So if you fail to keep the original image, then that means you will not be able to reconstruct the energy to a very accurate degree. Okay, so right, so my plan is to use machine learning, and my starting point is ChatGPT. So I asked ChatGPT to give me an example how to use neural network to remove the noise in an image. And this is what ChatGPT replied. It provided me a very simple convolutional neural network algorithm. As you can see, this is the entire model. It's very short. It is only like 20 or 30 lines. So I simply take this neural network provided by ChatGPT, and I apply that to my simulation data and see how this is doing. So this is the example we just saw in the previous slide. This is the input image. Actually, I trained the neural network with a lot of simulation. And after training, I provided this as an input to the convolutional neural network that's ChatGPT provided. This is the true, the ground truth answer. And this is the output from that ChatGPT neural network model. So it's very amazing, right?
So can you go back to the
Yeah.
slide? So that looks like a very low detail prompt to ChatGPT,
Yeah.
right? So how much work did you actually have to do on this?
No, I take this code literally from ChatGPT. I didn't do any change to the code. And this is the result. It's already.
So what is the input to the neural network?
What is the input to the neural network? Okay. Well, the input is this image. This is a two-dimensional. Well, think of this as a two-dimensional matrix. The matrix elements is just the count, the intensity in a pixel. And you provide this two-dimensional matrix to the convolutional neural network.
Yeah, go ahead.
No, Axel, you had a question?
Yeah, just typed it in the chat window. It's sort of related. The question is just like, how do you deal with the fact that the image grid is actually hexagonal? Because like native convolutions, as in PyTorch, for example, are defined on rectangular grids, right? So there's no native way to deal with that.
Yes. So my thought is how these pixels are arranged is actually not really important. You can either like take this image and divide this whole map with finer square pixels, or you can just say you can define a new coordinate frame where you can translate, do a distortion of this hexagonal coordinates into a Cartesian coordinate. But my thinking, my thought is that it doesn't really matter because this the information is about the rank of the matrix. So imagine if you have a 2D matrix, you can shuffle around the column or the rows, and that doesn't change the rank of the matrix. So it doesn't really matter how you arrange this pixel, as long as the arrangement for the pixels is consistent for all your data sets, then that should be fine. Well, sorry, I don't know if that answered the question. Well,
What is the loss, sorry for interrupting, what is the loss function, what are you training the neural network to do? What is the loss function that you are
Yes, okay.
training it on?
so the loss function is, well, you provide an input, the neural network will give you an output. The loss function is the difference between the ground truth image and the output of the neural network. Yes.
Just a quick question, when you actually had this problem of denoising the overall system and you switched to CNN and, machine learning, which is okay. I mean, did you actually try to look into options of simple filtering like a Gaussian filter or bilateral filter, just so that, or other your signal processing techniques that help denoising, which are more classical in nature? I mean, if the problem is only, remove noise out of your image, so if we can use, signal processing and those stuff, because those techniques are a lot more deterministic in their nature instead of something like machine learning, which has problems between just as a thought.
Well, I have not tried with like, well, you can even think this as like some kind of, you can design maybe a Fourier filter, filter out the high frequency part of the spectrum, and only the low frequency that will give you a large structure. But yeah, I have not tried that. Okay, so that was great. But the problem is when I trained this neural network, I was injecting the simulation with Gaussian noise. And so the neural network learned how to remove Gaussian noise very nicely, very impressively. But the problem with this approach is, just like I mentioned before, our noise is very dynamic, and we don't know the spectrum doesn't follow the Gaussian, and it changes the background distribution. The density function changes over time from hour to hour. So I did a simple test. Is instead of injecting the Gaussian noise, remember the neural network is trained with Gaussian noise, but what if my input image now the noise follows a non-Gaussian distribution? In this example, I'm using like this non-central chi-square function with degree of freedom equal to 2. So I correct the image with this non-Gaussian noise. And I provide this input to the neural network, and this is the output from the neural network. So this time, it no longer works. So the CNN is trained with Gaussian noise. It doesn't know how to remove the noise that doesn't follow a Gaussian density function. And this will be problematic because that means you don't know how to train the neural network to deal with the real noise. So the idea, the plan is just, okay, now I have this neural network who knows how to remove Gaussian noise perfectly. How can I make this neural network more universal to remove noise that follow an arbitrary function? So that's reflect what does it mean when you inject the noise into the image? So if you start with the clean signal image with no noise, that's P of X. So X is, for example, the intensity in a pixel without the presence of noise. And P is the probability density of this image signal. And when you inject noise, you are basically convolving this probability density with a kernel. And if the noise is Gaussian, then this is a Gaussian kernel. And the output of this convolution is your noisy image, the corrupted image. which is P of Y. So Y is the noisy image, which is the original true image plus noise. And our goal is trying to find an algorithm that can give you the expectation value of X. So you wanted to find out, given a noisy image, what is the expected value for X? So how do you do that? You, again, calculate the expectation value of X with this probability P of X given Y. You observe the Y, you observe the noisy image, and you're asking what is the probability for X. You can replace this part with P of Y given X with the base theory. However, to do this, you actually need to know P of X and P of Y. These are the priors, and you will never know the prior. So if you don't know the prior, then this formula is not very useful. So you might have known there's a recent very popular algorithm called denoising diffusion model for image generation. The idea for that method is basically saying that if you, sorry for that. If you have a corrupted image and your noise follows a Gaussian function, you take a gradient with respect to Y of this P of Y. If this noise term is a Gaussian, so you know how to do the derivative of the Gaussian that gives you this. Sigma is the width, the variance of the Gaussian function. And then you apply this base rule again to replace P of Y given X with P of X given Y. So a trick of doing this is that now you have P of Y in this integral with respect to X is basically a constant. So now you can move this P of Y outside of the integral. And if you move the P of Y outside the integral, then the left-hand side of the equation is this, as the gradient of P of Y divided by P of Y. And this will give you a gradient of log of P of Y. And on the right-hand side of the equation, the other side of the equation is this. So the second term, this again, Y is a constant in this integral. So then this entire thing is just simply Y for the second term. The first term is what we need, is the expectation of X given with the probability of X given Y. So on the right-hand side, we have what we want. This is the expectation value of X. And on the left-hand side equation is saying, in order to get what we want, we need to calculate the gradient of log of P of Y. So this now becomes something useful because remember we trained a neural network that knows how to remove Gaussian noise perfectly. So our neural network knows how to calculate because he knows how to find out the denoised image. That means the neural network knows how to calculate this gradient of log of P of Y if the noise is Gaussian. So that means we can develop some kind of iterative algorithm. If your noise, okay, so think about this as a space of your noisy image. You start with some initial position, and if this is a Gaussian noise, then the neural network will calculate the gradient of the density function, and that density function will tell you how to go from the noisy starting point to the denoised coordinate in one step. But if your noise is not Gaussian, the neural network will not tell you the correct gradient. But it will still tell you a direction that is more or less toward the direction where you need. So what you need to do is, instead of going from here to here in one step, because now this the noise doesn't follow Gaussian, but what you can do is you start with a noisy image at the initial point, and then you ask this neural network that knows how to calculate the gradient for a Gaussian function. You calculate the gradient and you move by a small step, because if you go this in one step, following this gradient, assuming the noise is a Gaussian, you will end up in a wrong solution. You don't want to do that, so you move only by a fraction of that, the estimation from the neural network. And once you arrive at the new coordinates, you ask the neural network to calculate the local gradient one more time. Now this time the neural network will tell you, oh, maybe you should move to this direction. So you take another small step following the updated gradient, and you continue doing this, then you will find a minimum that is much closer to what you need. So based on this, we can develop an algorithm. You have a noisy image and you want to build a model F. This F is your neural network that knows how to calculate the average, the expected point image that is proportional to this gradient. And we start with a noisy image of Y0, and the denoiser tells us how much step you need to take in order to remove the noise completely, but the denoiser only knows how to remove the Gaussian noise. So we don't trust the denoiser entirely. We will only take a fractional steps of what the denoiser tells us. For example, like 20%, 10%. You take a small step. And once you remove this small noise contribution, you ask the denoiser again with this updated image, in which direction I should move from my next step. And then you just repeated this process iteratively until you're satisfied with the final image. So let me show you how this is actually done with this example. All right, so this is the noisy input, and this is the true image. And this is the output from this neural network, assuming the noise is Gaussian, but this time the noise is not Gaussian, so the output from this CNN denoiser is just garbage. If you take this as one step, if you remove the noise in one step. So in this iterative procedure, we don't trust CNN entirely, but we still think the gradient is more or less correct. So we only take 10% of step. So we remove the noise for about 10% of the what the denoiser tells us. This is after one step, so it's still very noisy. But if you repeat doing this, this is after 14 steps. We can already see there's an improvement. And then this is after 28 steps. Now you can arrive to a much better denoised image, even though your denoiser is trained with Gaussian noise. Yes.
Again, let's go back to the previous slide. Where's that image? So you are kind of training yourself to, taking 10% of whatever the lens and then finally somehow writing it to the. So is this like the local minima, or are you kind of dealing with that aspect, or let's say if you initially went into a little bit wrong direction, but you didn't go too far, but that actually led you to a different, the local minima.
Yeah, I think that's possible. But what I'm assuming here is if you take this iteratively, the closest minimum is the true global.
So this specifically, there is only one minimum, but if let's say there were two minima, chances are that it could go either one of them. And it could be that the one of them could be non-participating. Just like.
Yeah, I think that's totally possible. But so far this works very nicely for me. Okay, right, so that was in like a toy simulation. I injected some random non-Gaussian noise. And now I tested this with a more realistic simulation from CTAO. So CTAO did measurements on the night sky background, I believe, from the site, and then they produced some more realistic noisy simulation. And this is using this simulation. This is the input noisy image. You have the shower here corrupted with some realistic noise simulation. And this is the output from the original denoiser. If the denoiser thinks the noise follows a Gaussian noise, and of course it doesn't, you get a very you get a trash output. And this is using the same denoiser, but now this time you do this with this iterative small step procedure. Right, so this is just I provide 3 examples to show you.
So this is, you said this is real data or also
No,
simulation?
well, for CTAO, we don't have real data
Oh, okay,
yet,
so
so this is still simulation.
Okay, okay.
But we do have plan to do this with real data. So this method is based on this paper called Solving Linear Inverse Problems with prior implicit in the denoiser. And well, the reason that the author says this is prior implicit because what you are calculating, well, what's the neural network is calculating is not really the prior, but the gradient of log of the prior. Okay, yeah, so we do have plan to test this method with real data, but not from CTAO, but from Veritas, and we will evaluate how much we can gain from this methods by, for example, looking at if we can improve the gamma ray angular resolution by doing the denoising using this iterative procedure, and if we can improve reconstruction efficiency and detection significance, for example. Okay, so now I'm going to enter to the next part of the talk is about time domain gamma ray astrophysics using machine learning. So for this part, this is kind of very preliminary project. Well, because this is a machine learning community, so I try to put together some machine learning projects that I have been thinking, although this is not very mature. So if you have feedbacks, I welcome all your feedback on this subject. Okay, so why do we care about time domain astrophysics in high energy gamma ray, for example? One of the, well, this is the spectrum of cosmic rays. You know, the cosmic rays basically follow a power law with the spectral index of 2.7, all the way until some energy threshold at about 4 PeV. And after that, you see a softening of the spectrum of the cosmic ray. So this feature, people believe this feature tells you there's a energy threshold, maximum energy, where for the sources, the accelerators in our galaxy can achieve. So a major task, a major goal for gamma astronomy is to, for example, identify where these PEV accelerators are located in our galaxy and how do they manage to accelerate particles up to this high energy. And variable source like gamma ray binaries are ideal laboratory for this kind of study because they provide varying but repeating conditions for the acceleration. So you can, for example, look at the light curve of the gamma emission and try to predict, try to constrain the models for particle accelerations. And this is doing this from a variable source in time domain is maybe much more interesting than analyzing a stationary, a stable source that doesn't change over time. And a very interesting example of this kind of source is this SJ0632. So this is a source with a periodicity of about 300 days. And here I'm showing you this is the light curve of this source in the X-ray band. And on the bottom plot, this is the light curve in the gamma ray energy band. So you can see there's a high degree of correlation between the light curve that you detected in the X-ray band versus the light curve in the gamma ray band. And in addition to this periodic flares, for this source, there were also two outbursts happened. The first one happened in 2011, second one happened in 2010. These outbursts, they produced the highest flux ever recorded from this source. So this will mean that in addition to this 300 days period, there is additional hidden complex structure that we don't understand yet about this about the binary system. Furthermore, the emission from the source peaks at PeV. That means we detected the source in X-ray and also brightly in gamma ray, but the Fermi-led telescope doesn't detect the source with high significance. It's very faint in Fermi data. So this will imply that there's maybe a larger population of this kind of source that is faint in GeV but very bright in PeV. And this gives this means with future CTA, we will have much better sensitivity in detecting more this type of source in the future. Right, so the challenge for this kind of time domain VHE, very high energy astrophysics is that our current trigger depends on the alert from lower energy observations. So for example, if you observed some flare from some source, for example, from an X-ray telescope or from Fermi-led, then you send an alert to IACT observatories, and then IACT follow up the source after they receive the alert. IACT telescopes, they have very small field of view, about 4 degrees in diameter. So this makes IACT disadvantageous when you try to detect time-sensitive events, because you needed to know exactly where the event is in the sky, and you need to swing your telescope to that direction accordingly. And also, the source power law spectra and like I mentioned, the current generation typically only have like 4 or 5 telescopes. Their effective area is very small, so this also makes the current IACT observatory insensitive to weak variabilities. So in the future, when CTAO comes online, we would like to have some kind of predictive model in order to catch these transients in time, or make some target lists for future observations. To make this kind of prediction for VHV transients will require knowledge about discover repeat hidden patterns in the past observation. If you have already observed the source in the past time, maybe you can use this historical data to predict when the next burst of flare will happen. And we also need, because very often we rely on low energy observation to make a trigger for transient. You also need this knowledge about the correlation between the low energy flare, high energy flare. So you need at least these two factors in order to make a prediction for VHV transient. So now I'm going to talk about some premature.
Letting you know that you have 7 minutes left, including any questions remaining.
Oh, okay, then I will try to finish this fast. All right. So the flare, time domain astrophysics. For example, this is the current state of the source, and then maybe the next day, the system moved to the next state, the different states that can produce burst emission. And this dynamics can be nonlinear and chaotic. So it's difficult to model this kind of system. And there's a theory called a Koopman operator. The idea is that if you find a mapping that you can map the observed the state of the system to another system, to another dimension, another space. So you make a map going from X to Y, and in this Y space, then you will find this system to be linear, to be described by a linear system. So the idea is that you bring this nonlinear system in a finite dimension, and you map the system to a linear space, but with infinite dimension. And if in this infinite linear dimension space, if the matrix is low rank, that means you can truncate the matrix and make a good approximation of that linear system. So this is an example of a chaotic system, the Lorentz system. You have basically two different states, metastable states in this chaotic system. You have sometimes the system stay in this space, and sometimes the system lives in this space. So you plot this trajectory of the system as function of time. So now imagine this is like a light curve of a transient source. Sometimes you have elevated emissions. Sometimes you are in this quiescent state. And if you can find a way to using a linear system to approximate this nonlinear chaotic system, basically this method is saying you like vectorize this light curve into a matrix. So the first row of the matrix is your light curve, and then the second row is still the light curve, but now you shifted this by a time difference. And once you construct, so each row is an increase in time of the light curve. And then once you construct this matrix, you do a linear decomposition, singular value decomposition. And what you will get, hopefully, is that you will find some principal component that can well describe your nonlinear system. But of course, because this is a chaotic nonlinear system, you will never have a perfect description of the system with a linear approximation. So you will have some residual that is not a good fit to your nonlinear system. But in this method, what important is this residual is that if you look at the residual and this, for example, this is the first few eigenvector that can describe the system well with some linear approximation. And the residual tells you, for example, this is when you see if there's a sudden large residual, it tells you the system is about to switch to a different state. So here, this paper color-coded the large, when the large residual happens, is in red. So when you see this peak and this residual factor, that tells you the system is about to do a transition from, for example, a quiescent state to a burst state. So in this example is that the system will stay in this state for a long time until at some point, at this point B, you started to see a large component from this residual vector. This means the system is about to make a jump to a different state. So this framework might be useful to make a prediction. Is that by doing this analysis of the Likert from the past history data, if you see there is a sudden increase in this residual vector, this will tell you maybe the system is about to jump to a different state, and that's when you should send an alert to the pointing telescope to observe the source before the burst occurs. Okay, so do I still have time?
Well, 2 minutes. So
Okay, then I can stop here then.
all right. Well, thank you very much. We have more questions. Ruo-Yu. Yeah, what is the linear
Like in these last part, when you take out all the singular value, what is it called?
Okay, so, well, okay, first, this matrix is basically, so each row here is, for example, imagine this is a line curve of the source. So each row is a line curve. And your goal is to, for example, your history data, your past data ends here. You want to predict what happens next, right? So what you can do is that you shift your entire history data by 1 unit, and then you put this shifted line curve to the second row, and then you shift by another unit, and you put it in here. So now let's call this matrix H. So the idea is that imagine that you wanted to make a new prediction for a new row in the future. That will give you a new time step in the future. And you hope this matrix can be described by a linear system. That means when you, okay, so when you wanted to make a jump from here to here, this jump can be described by a linear equation. You wanted to find out this operator K that can, basically this is a linear operation that your future states can be well described by this linear matrix multiplication. So this SVD is basically trying to model this system with some linear approximation. And so, well, if you, so this matrix sigma here, this is the singular value matrix. If the singular value is large, that means this vector here is an important component for your system. Your system will be largely captured by the vector correspond to the largest singular value. And in order to make a better approximation, you need to add more and more vector. But more vector you add, you are adding vectors with smaller and smaller singular value until some point. The singular value is so small that means you don't really You don't really do much better by including the residual vectors to this approximation. However, the residual vector is still important because when there's a huge change in the residual vector, it basically tells you this system is no longer stable, it's about to jump to a different state. Right.
All right, well, I think we ran out of time and I want to let people continue with the day. So Ruo will be today in 412 in the B building if anyone wants to talk to him. Other than that, let's thank him again. Thank you.